Hello and welcome to Brook Abhyantriks. Again, in today's video we are going to talk about composite bars and effect of temperature on the composite bar, and also we'll discuss a special case in this. Alright, so we'll deal with first question now. A composite bar shown in the below figure is rigidly held between two unyielding supports. Find the stresses in each material when the temperature is raised by the amount of 50 degrees Celsius. So they have given T as 50. We shall take E for aluminium as 0.7 into 10 to the power of 5 Newton per mm square, and E for steel is given as 2 into 10 to the power of 5 Newton per mm square respectively, and they have also given alpha A and alpha S. Right, so a fairly straightforward problem. Now when we'll have to see whether there is an external load acting on it. So if there is an external load, we'll have to consider two cases, one with the external load and one without the external load and only the temperature. Now in the first case, we'll only talk about the load, the external load which is acting upon it. Now with this we can write the static equation for this. So now at the support A, let's say, so we are going to have reaction something like this. So I'll call this as A, and I'll call this interface as B, and I'll call this face as C, and at C I'm going to have reactive force something like this. Right, so now if I write the equation, I'm going to have the static equilibrium equation. I'm going to have RA plus RC will be given as 200 into 10 to the power of 3, and I'll call this as equation number 1. Okay, so now if I write the free body diagram for all the sections here, so for the aluminium body it will look something like this. So this is going to experience tensile loads. So the load here is RA. So this is what we are going to find out here. The length is 100, and and about the steel body now. So for this, again we are going to experience tensile load, and this value will be equal to RA minus 200. Right, so I'll keep everything in kilonewton itself so it won't be confusing now, and this will be again RA minus 200. Right, so now with this, since the supports are unyielding, we can write that delta AB plus delta BC is equal to 0, now which is nothing but RA into the length, which is nothing but 100, divided by the area, so which is nothing but 1000 again, into 0.7 into 10 to the power of 5. So I think the data is missing in this particular equation. So here the area is 1000 mm square. So here the area is 1500 mm square. So this the data was missed out while typing out the question, sorry for that. Now plus RA minus 200 into 150, the length of the second body, so divided by 1500 into 2 into 10 to the power of 5 will be equal to 0. Now if I simplify this, I'll be getting RA as 51.85 kilonewton. Now RC is nothing but RA minus 200, so which will be equal to minus 148.18 kilonewton. Sorry, kilonewton. Right, so now what would be the stress on the aluminium body? Sigma A, that is nothing but the load RA, that is RA by the area of aluminium is 1000, so which would give me plus 51.85 Newton per mm square. Right, so this is tensile. So what about the steel body? In the steel bar. So I'm going to have sigma s is given by the RC value, so which is nothing but minus 148.15 divided by the area of the steel bar, so that is nothing but 1500. So which would give me, so this is into 10 to the power of 3, this is in kilonewton, right? So which would give me minus 98.76 Newton per mm square. So this is compression, right? So now we have the second case. In the second case, we are going to consider the stress developed due to the temperature, right? I'll write it as due to temp, right? So I'll write a short diagram for this. So this would look something like this, right? So we have the fixed ends here, and what kind of stresses would these two develop? So these two both will again develop compressive loads or compressive stresses here, right? So how exactly are we going to solve? First of all, we are going to equate the loads or the forces which will be acting upon these two bodies, that is FA will be equal to Fs, so which is nothing but sigma A into area A is equal to sigma S into AS. Now if I substitute this here, I'll have 1000, so here I'll have 1500, so which is nothing but sigma A is given by 1.5 into sigma S, and I'll call this as equation number 2. Now again, since the ends are fixed, I'll have delta AB plus delta BC will be equal to 0. Now the free expansion of AB because of the rising temperature is given by LA alpha A into T. And now what about the stress? We are going to experience compressive stress, so that is minus sigma A into LA divided by EA plus again free expansion of the aluminium body steel LS into alpha S into T minus sigma S LS divided by ES will be equal to 0. Now if I substitute here, I'll have 100 into 24 into 10 to the power of minus 6 into 50 minus sigma A, this is what we will have to find out, into 100 whole divided by 0.7 into 10 to the power of 5 plus the steel length is 150 into 12 into 10 to the power of minus 6 into 50 minus sigma S into 150 divided by 2 into 10 to the power of 5 whole, everything would be equal to 0. Now if I simplify this, I'm going to get 1.43 sigma A plus 0.75 sigma S will be equal to 210. Now with the help of equation number 2, if I substitute here again, I'm going to get sigma S will be equal to 72.5 Newton per mm square. Alright, so this is again compression, right? So just for the sign convention, I'm going to write minus here. What about sigma A now? And if I substitute this back in equation number 2, I can find out the sigma A, which gives me minus 108.75. I have deliberately added the minus here just for the sign convention. So since we have compressive load here, so that's why I've added minus. So what about the total stress now? So the total stress is going to be, for sigma aluminium, I'm going to have 51.85. So the stress due to load, this guy, minus 108.75, which gives me a total of minus 57.07 Newton per mm square. So for steel, now I'll have due to load, I'll have minus 98.76 minus 72.5. I'm going to end up with minus 171.37 Newton per mm square. So this is going to be the total stress, compressive stress, that is going to be acted on the body because of both direct load as well as the temperature. Now moving on with the next problem or the next special case. So we are going to analyze a bolt assembly which is holding down a copper tube. Right, so here we have a bolt which is holding down the copper tube. So what is going to happen if I tighten the nut here? So if I tighten the nut, the tube will be experiencing compressive force. So what about the bolt? The bolt is going to elongate. Right, so this is how we are going to deal with this problem. So this, instead of a bolt and a tube, so we are going to consider this as again a composite bar. Alright, so now the case 1, if we are tightening a bolt or tightening the nut by theta degree. Right, so now what would be the total number of turns? The total number of turns of the nut is given by theta divided by 360. Right, so now what would be the axial movement? The axial movement will be given by n into p. So here p is the pitch of the thread. Right, so and for equilibrium we are going to write again two different equations to solve the problem. And for equilibrium we are going to have the forces experienced by the bolt will be equal to the forces experienced by the tube. Now if I talk about if the tube is made up of copper and the bolt is made up of steel, so I'm going to end up with sigma s as will be equal to sigma c into ac. So this will be my first equation. The second equation is what would be the total deflection. The deflection is already found out, that is np. Np would be equal to the delta s plus delta c. So again, which would be nothing but sigma s ls divided by es plus sigma c lc by ec. So this would be my equation number 2. So with these two equations I can find out the stresses and the loads. Now what about the temperature? So now since the alpha of copper will be greater than alpha of steel, the copper is going to experience compressive load and the steel or the bolt is going to experience tension. Right, so now again we are going to use same two equations, that is force taken up by the copper or the tube will be equal to the force taken up by the bolt, so which is nothing but steel. So again, whatever the total deflection of tube will be equal to the total deflection of the steel. So this is where we will deviate from the first case. Right, so again with these two equations we are going to again solve the problem. So here the free expansion, that is L alpha Ct, because of the compression in the copper or the higher coefficient material, we are going to have compressive load here, sigma c into L divided by Ec. Now that will be equal to the free expansion of the bolt, that is L into alpha s into T. Now I'm going to have tension here, so plus sigma s into L divided by E into S. So this would be equation number 2. Sorry, equation number 3. So with all these equations we can solve the total stress that has been developed by the nut by the bolt and the tube because of the rising temperature and because of the torque that has been applied to it. Right, so with this knowledge, let me solve one problem on this. A steel bolt of dia 10 mm passes through a brass tube of internal dia 15 mm. Right, so I'll have the diameter for the bolt, the steel bolt, I'll call this as ds, that is 10 mm, and for a brass tube, so here the internal diameter is given as 15 mm and the outer diameter is given as 25 mm. Right, so the bolt is tightened by a nut such that the length of the tube is reduced by, the delta is given as 1.5 mm. If the temperature of the assembly is raised by 40 degrees Celsius, T is 40 degrees Celsius, then estimate the axial stress in the bolt assuming the length of the tube. L is given as 1500 mm. So they have also given ES and EB, alpha S and alpha B. Right, so with all this prior data, let me solve the problem here. Now if I let me just do some calculations for the area first. What about the area for the bolt? So for the bolt, I'm going to have pi by 4 into the diameter square, that is 10 square. So I'm going to end up with 78.54 mm square. And for the copper cross-sectional area of the tube, I'll call this as AB, will be given by pi by 4 into outer diameter square, that is 25 square, minus inner diameter square, 15 square. So I'm going to end up with 314.16 mm square. Right, so now first case, I'm going to neglect the temperature. I'm only going to talk about the tightening. So I'm going to go with tightening of nut. So what is going to be this for stresses experienced by this? So first of all, I'm going to equate the forces between the copper and the brass. I'm going to have sigma S1 into A1 is equal to sigma B1 into A1. Now, if I substitute the AS and AB, so if I substitute the values of A for this expression, I'm going to end up with sigma S1 is equal to 4 sigma B1, equation number 1. Right, so now they have also given us delta is given by 1.5 mm. So delta, if I expand this, sigma S1 by S into L plus sigma B1 divided by EB into L is given by 1.5. Right, so if I simplify this, again substituting by equation 1, so I'll end up with sigma B1 as 33.33 Newton per mm square, and this is a compressive load. Because if we tighten the nut, the tube is going to be compressed. The bolt which is made up of steel will be in tension. So again, if I substitute the sigma B1 value in equation number 1, I'm going to end up with sigma S1 as 133.33 Newton per mm square. So I'll use the signs here. So minus and plus. So this is in tension. Right, now I'm going to talk about the effect of temperature. So effect of temperature on this bolt and nut assembly. Now first of all, I'm going to use the equilibrium equation, that is equating the forces. I'm going to have sigma S2, that is the stress on the bolt, into the AS is equal to sigma B2 into AB. So if I substitute the value of AS and AB in this, again I'm going to end up with sigma S2 is equal to 4 sigma B2. I'll call this as equation number 2. And again in this, since we know that alpha of brass is greater than alpha of steel, the brass will have compression. The brass will experience compressive stress. The steel, which is the bolt, is going to experience tension. So we'll have the rise in temperature, right? So now the second set of equations, compatibility equations, is going to be given by sigma or delta S. The deflection in steel is nothing but the deflection in the tube. Now the free expansion of steel, L alpha S T. Now we'll have tension in this, plus sigma S2 into L divided by S will be equal to the free expansion of the tube, L into alpha B into T minus sigma B2 into L divided by EB. Now if I substitute all the values, all of these values except these two are known, and I can make use of equation number 2 to substitute one of these in terms of other. I can find out sigma B2 as 9.33 Newton per mm square. So this is compression because it is made up of brass. And for steel, again if I substitute this value in equation number 2, I'm going to end up with 37.33 Newton per mm square. This is tension and this is compression. Now the total stress is going to be sigma s will be equal to sigma s1 plus sigma s2, and if I sum it up, I'm going to end up with minus 42.66 Newton per mm square. So this is compression, and sigma b will be equal to sigma b1 plus sigma b2, which is nothing but 170.66 Newton per mm square. So this is tension. Alright, so hopefully this video has been helpful for you. Thank you for watching our video. Please like, share and subscribe. See you in the next video. Happy learning.